Great, so moving on. So now we have the ultimate and final rule for Lewis structure, and that's called the formal charge, okay? So formal charge, let me see, yep, I got examples coming up. So formal charge is used to evaluate the best Lewis structures, particularly for atoms exceeding the octet rule, okay? And so formal charge has an equation right here, and the equation goes number of valence electrons, and we do this formal charge for each atom, okay? So this would be for each atom, just its number of valence electrons that we get right off the periodic table, okay? And now this is going to be minus, now for this atom, right, for each atom, really I should point it to there, okay? It's going to be the number of unshared electrons plus 1/2 the number of bonding electrons. And notice that's not the number of pairs, it's the number of electrons. So I have a really easy way to remember this crazy formula. Number of unshared electrons plus 1/2 the number of bonding electrons. It's dots for this chunk plus sticks for that chunk, right? Because if you think about it, 1/2 the number of bonding electrons just gives you the number of bonds, right? Because there's 2 electrons in each bond. So when you take 1/2 of that, you're really just counting up the dots plus the sticks. Okay, so it's an easy way to remember it. Valence electrons minus, and remember, so this is like all in a parentheses together. So we get that negative sign distributed through correctly. Number of valence electrons minus dots plus sticks. Easy. Okay. So rules. The sum of the formal charges on all atoms in a given molecular ion must equal the total charge. So if something is neutral, if it's completely neutral, all of those formal charges have to add up to 0. However, if it's a polyatomic ion, like nitrate, for example, nitrate is -1. All of the formal charges have to add up then to -1, to whatever its charge is. Okay. Number 2, if non-equivalent Lewis structures exist, those with formal charges closest to 0 are good, and negative formal charges on the most electronegative elements are also considered good. So for example, if you draw up a structure and then something like, oxygen or fluorine has a +1 formal charge, that's no bueno. Oxygen and fluorine are super electronegative. They don't want to be positive. They want to be negative. Okay? So let's do some examples. And there's 2 really good ones. And sulfate and phosphate. And these are ubiquitous. So these are very common. Okay? So now, let's do all the rules that we know. Okay? And so that is, we add up the valence electrons. So sulfur is 1, 2, 3, 4, 5, 6, plus 4 oxygens, and each one of them are also 6, plus 2 extra for the negative charge. Okay? And what we get out of that is, let's see, 24 plus 6 makes 32, so that's 32. Okay, so now we do Clark's rule. And Clark's rule says 6, so 5 non-hydrogen atoms plus 2, and that equals 32. Huh. So what's the deal, man? Why am I using this as an example? Because this just says we should be good to go, right? This says we expect it that it's just going to be all single bonds. Okay. Let me make this much bigger. Oops. So the Clark's rule says we should all have single bonds. And if I go and do all of the right lone pairs, if I fill them all around, and I consider that this whole thing is -2, then this should be the Lewis structure, right? This is what you would expect. But chemistry is the science of exceptions. So now I'm going to do the formal charges. of this structure, and we're going to see if that's the best possible structure. Okay? So let's first do the sulfur. Okay? So the sulfur is valence electrons are 6, and it's minus dots plus sticks. Okay? So this sulfur doesn't have any dots, so that's 0, plus sticks, 1, 2, 3, 4. All right? So that equals a positive 2. So this tells me the formal charge on just this sulfur is a positive 2. Okay? So when you're doing some homework assignments and they ask you to include formal charges, and I'm going to go through this in a discussion on Tuesday, you have to add that plus 2 to the sulfur. Okay? You have to indicate that that sulfur is plus 2. So now what about oxygen? Well, we only have to do it for 1 because all 4 of these oxygens are equivalent. And we know oxygen has 6 valence electrons. And now minus dots. So 1, 2, 3, 4, 5, 6 dots. Okay. Plus 1 stick. And so 6 minus 7 equals -1. So that's good that we got a negative for oxygen because oxygen is electronegative. And we note all of these oxygens are equivalent, okay? So this is -1, this is -1, this is -1, and this is -1. And in fact, all of those would add up to the -2 charge on sulfur, right? Plus 2, -1, -1, -1, -1, gives me -2. However, this is not the best Lewis structure, okay? And I'll show you why. So now I don't have any predictive way of telling you how to arrive at the best Lewis structure, but I'll just show you what is the observed Lewis structure, and I'll tell you why it's the observed Lewis structure. So as it turns out, without using anything of Clark's rule, we can make a better Lewis structure for this thing by doing the following. Just 2. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. This, as it turns out, is the best Lewis structure. Okay? And this is why. So now if I go to do the formal charges now, okay? And you notice we've made Texas sulfur. We expanded the valency of sulfur, right? We busted the octet rule. But we can do that for sulfur. Remember the compound SF6, let's find it, right? SF6 is a stable compound that it consists with sulfur taking 12 electrons. And here sulfur has taken 2, 4, 6, 8, 10, 12 electrons. So we know it can do it. So now if I count up the formal charge of this sulfur, it's still 6 valence electrons minus 0 dots. However, now it's got 6 sticks. That gives me a formal charge of 0. And for the central atom, a formal charge of 0 is much better than a formal charge of plus 2. So we've already improved that. Okay? Now, what about the double bonded oxygen? So I'll draw that by saying double bonded oxygen. Okay? So what is its formal charge? All right? Well, it's still 6 valence electrons for each oxygen. And it's got 1, 2, 3, 4 dots. Plus 1, 2 sticks. So 6 minus 6 equals 0, so that's great. And this is something really important to note here. Okay, you don't have to memorize this, but if you're a chemistry major, maybe this is a good thing to commit to memory. Whenever you have a double bonded oxygen like this, and it doesn't matter what it's bonded to, so that's why I kind of drew that squiggly. A double bonded oxygen always has a formal charge of 0. Always, no matter what it's bonded to, right? Because when we counted up this formal charge, we didn't consider what it's bonded to. So double bonded oxygens always have formal charges of 0. All right, what about my single bonded oxygens? Okay. Oops, let's indicate that on there, right? That's a 0 formal charge, and that's a 0 formal charge, and that's a 0 formal charge. Okay. So now my single bonded oxygen, which I'll draw like that, still 6 valence electrons, minus, and now there's 1, 2, 3, 4, 5, 6 dots plus 1 stick. So that's -1, and which we came up with the same thing over here, right? So another good rule of thumb is all single bonded oxygens always have formal charges of -1. So now this has a -1, and this has a -1, and 0 plus 0 plus 0 plus -1 plus -1 will give me -2. Okay? So now how do I know that this is the correct observed Lewis structure of sulfate? Well, check it out, okay? We know that sulfate, when you add, let's say, 2H plus SO4 2 minus, we make sulfuric acid, H2SO4, right? So why is it that it takes exactly 2 hydrogens? Because of the -1 oxygens, right? So H2SO4, sulfuric acid, has a Lewis structure that looks like this, okay? With the hydrogens bonded to those singly bonded oxygens, because these singly bonded oxygens are -1, all right? So they're perfect. They're primed and ready to take on 2 hydrogens in the case of sulfuric acid. So that's how we know that this is the observed Lewis structure of sulfate, because of the way the hydrogens bond. Okay, so now I want you to try phosphate on your own. I'm going to put it on the discussion worksheet so you'll get a chance to do it. But see if you can come up with what the best Lewis structure for phosphate is. And I'll give you a hint. We know that when we add 3 hydrogens to this thing, right? If I say 3H plus 1 phosphate, we make phosphoric acid. So it seems reasonable that there's probably 3 single bonded oxygens and 1 double bonded oxygen. See if you can come up with that on your own. Okay? I'm going to move on to the next